Olá, pessoal. Boa noite. Tudo bem? Bem-vindos e bem-vindas. Good evening. Welcome, everybody. Bom, eu sou Elisa Rocha Barbosa, atual diretora presidenta da Sociedade Brasileira de Geologia, e hoje, junto com o nosso primeiro secretário, Murilo Medeiros, damos início às comemorações dos 80 anos da SBG, com a estreia da série Giro pelas Américas, com a SBG. A Sociedade Brasileira de Geologia agradece gentilmente o patrocínio do Sistema Confé para a realização dessa série de lives. A primeira reunião da SBG foi realizada por um grupo de jovens geocientistas em São Paulo, com o objetivo de criar uma sociedade científica de geologia, e aconteceu em 6 de maio de 1945. Em 27 de dezembro deste ano, foi então formalizada a fundação da SBG, quando foi definida uma comissão para a redação do Estatuto. Em abril de 46, foi formalmente eleita e empossada a primeira diretoria. E para celebrar este histórico importante, nós programamos eventos especiais, que iniciou hoje, 29 de setembro de 2025, e esses eventos vão culminar na festa de aniversário de 80 anos da SBG, que vai ocorrer durante o Congresso Brasileiro de Geologia, de 1 a 5 de novembro de 2026, em Fortaleza, no Centro de Eventos do Ceará. Então, reservem a data, estão todos convidados. Ao longo do segundo semestre, faremos um conjunto de apresentações divididas em 2 séries, uma online e uma híbrida, para juntos celebrarmos a nossa paixão, a geologia. Então, iniciamos nossa viagem com a Geological Society of America, cuja parceria importante entre a SBG e a GSA foi celebrada recentemente por meio de um memorando de entendimento para promover nossos objetivos compartilhados de avanço nas descobertas em geociências e apoio às profissões geocientíficas. E hoje temos aqui o presidente da GSA, professor Nathan Naime, e a doutora Esther Stern, não sei se pronunciei direito, que é a diretora da parte internacional, né, de relações internacionais da GSA, e temos o prazer aqui de contar com a Esther para nos dar algumas palavras sobre esse assunto. We begin our journey with the Geological Society of America, whose important partnership between the SBG and the GSA was recently celebrated through a memorandum of understanding to promote our shared goals of advancing geoscience discoveries and supporting the geoscience professions. So I invite for some words our dear Esther Stern, which was very important to build this partnership. Thank you so much for coming, Esther.
Muito obrigada, Elisa. Boa noite a todos. Vou dizer umas poucas palavras em português, depois vou mudar para o inglês. Estou muito contente dessa nossa nova parceria e eu espero que esta seja a primeira das atividades a compartilhar, desenvolver para fazer realidade esta parceria. Hello, everyone. I am very happy that I'm here, that we are here all together to celebrate our new links with the Sociedade Brasileira de Geologia. And I wanted to say a few things. We have 89 associated societies 37 are international. For us, international is a very important part of what we do and who we are. I wanted to mention that we have a series of activities that we do in a partnership alone or in partnership with others. We have webinars like this one. We have international travel awards programs. We have other senior and junior awards for research. We recognize people in the whole life cycle of their careers, and more to come later on that. I wanted also to mention that among the international activities we do are the international field fora. The Thompson Field Forum earlier this year, was in Cuba. Next year, we are organizing, not just planning, we are organizing one in Nepal and one in Namibia, so maybe we can do one in Brazil. And we have the Thompson Lectures, which are a distinguished award that is given for lecturers to come from abroad to the US, including Brazil, and US scientists to give lectures abroad. So there is many things that you can participate. There are many things you can participate in, and this is the first one. Nathan?
Thank you, Esther. I just want to echo Esther's comments about how important working with international geological associations is to GSA's work. We recently signed the Memorandum of Understanding with SBG. I had the opportunity to be at the meeting in Belo Horizonte in October, almost a year ago, and very much enjoyed that. And so we really look forward to building our partnerships with international geoscientists all around the world. I can say a little bit about GSA. GSA has 17,000 members, many in the United States, Mexico, and Canada, but also around the world. We have multiple meetings each year with a flagship annual meeting that takes place in various cities around the United States, and then sectional meetings that take place in different portions of the United States each spring. We have scientific publications to advance the science and research in the geology, including journals such as Geology and GSA Bulletin. And we do, as Esther said, field forums where we take groups of scientists around the world. Nepal and Namibia are coming up this year. We also have Penrose conferences, which are small conferences focused on very specific topics to bring together leaders in the field to talk in small groups. And this year we will actually have, I think, a Penrose conference in Iowa in the United States to talk about the advances in geochronology. And so we do all these various activities, connects meetings, scientific publications, smaller meetings to bring together earth scientists and to really advance the scientific mission of the geosciences. Lastly, we play a really big role in bringing in student members. A significant number of GSA's members are students, undergraduate and graduate students. Mentoring them, introducing them to the profession, launching them on their careers, and keeping them as members as they go on into industry, academia, or government to pursue work in the geosciences. And GSA has also moved this year into a popular book series. Within the United States, we publish accessible books on geology of all of the states of the U.S. and specific regions of geological interest, such as national parks, that are designed for an audience who may not have a strong scientific background to learn something about the geology all around them. So, thanks.
Thanks. I was thinking if I put that slide or not when you were talking.
That's okay.
But okay. Thanks so much, Nathan.
Sure.
And here is Professor Nathan NIEMI, GSA President, who will give us a lecture entitled Geological Evolution of the Grand Canyon, Arizona, USA, and the controversies surrounding the timing of its formation. I now invite Murilo to introduce us to the distinguished speaker. Thank you, Murilo. Obrigada, Murilo. Por favor, nos introduz agora o professor Nathan, que vai nos fazer a palestra. Muito obrigada. Valeu, meu caro.
Por nada. So sorry, Nathan, I'll speak a little bit in Portuguese, introduce you for our public. And I'm going to read, so if you understand a bit of Portuguese, you can correct me if something is not right, ok? So, boa noite, pessoal. Vou apresentar aqui o nosso palestrante de hoje. Nathan é professor titular no Departamento de Ciências da Terra e Ambientais da Universidade de Michigan, nos Estados Unidos, e pesquisador associado ao Programa de Meio Ambiente da mesma instituição. Ele é geólogo, formado em Ciências Geológicas pela Universidade de Cornell, e obteve os títulos de mestre e doutor em Geologia pelo Instituto da Califórnia, Caltech. É diretor do Camp Davis Rocky Mountain Field Station desde 2013, um centro de campo voltado à formação prática de estudantes em geociências. Seus principais projetos de pesquisa envolvem a evolução tectônica de grandes sistemas orogênicos, como o norte do Tibete, a região do Cáucaso e a província Basin Range, no oeste dos Estados Unidos. Trabalha com reconstrução paleogeográfica, datação de eventos tectônicos e modelagem de processos de deformação da crosta terrestre ao longo de milhões de anos. Sua atuação combina análise de dados geológicos com trabalho de campo em regiões montanhosas e tecnicamente ativas ao redor do mundo. Tectonicamente ativas. O professor NIEMI é reconhecido internacionalmente por suas contribuições à geologia estrutural e à geodinâmica. Foi eleito membro da Geological Society of America, GSA, em 2014, e da American Association for the Advancement of Science em 2019. Atuou como editor da revista científica Tectonics e participa ativamente de comitês acadêmicos, bancas e processos de avaliação de agências de fomento, como a National Science Foundation. E é isso. It's a long curriculum, long experience. Very good.
Obrigada, Murilo. E realmente, então vamos agora aproveitar aí a nossa palestra. Vou colocar aqui a tela e agradecer mais uma vez aí a presença de todos. Acho que no YouTube é possível ativar a tradução, não é? Simultânea. Então é uma vantagem. Vamos testar aí, pessoal do chat, por favor, avisa se deu certo, como é que tá indo. So, please, Nathan, when you want to.
All right. Well,
thanks
thank
so
you
much.
so much for having me, Elisa and Murilo. And I'm glad to be here to celebrate, I think it's SBG's 80th anniversary as a scientific society, and to take part in their Tour of the Americas lecture and webinar series. When I was thinking about what to talk about, I really couldn't think of anything that was much more iconic geologically than the Grand Canyon in the United States. And if one was going to take a tour of the United States and look at geology, the Grand Canyon would be an essential place one would have to stop and see. As Murilo said, I've worked in the Western United States for most of my career. I particularly work in Nevada and Utah, which is an area of the Western United States called the Basin and Range. But immediately adjacent to that sits an area called the Colorado Plateau, and that is where the Grand Canyon is located. So I am not an expert on this, but I know a bit, and I hope I know enough to share some interesting things with you about the Grand Canyon. But I thought I'd start with a little bit of history. The Grand Canyon, as I mentioned, lies in the state of Arizona, which is in the western U.S. Like Brazil, the United States is a significantly large country, and for much of its early history, the population of immigrants who came from Europe lived on the eastern side of the United States. Obviously, there were indigenous peoples across the United States, including all throughout the Western United States and the area I'll be talking about today, who would have known and seen many of the things that we'll be discussing. But the kind of popularity of the Western United States within the population centers in the East came about in the late 1800s. The Civil War had ended in the United States, and Americans began to move west and expand into territory that was not particularly well known or well studied. Certainly, as I said, indigenous peoples had lived there. Spanish explorers had come up from Mexico. Fur traders and trappers had moved through this part of the world, but there hadn't really been some systematic study of this part of the country in terms of its geology, its biology, its physiography. And so in the aftermath of the Civil War, 4 major surveys were announced and funded by the US government to explore and understand the Western United States. The names on these probably won't mean a lot to people in Brazil, but they became influential geologists in the Western US. And one was Clarence King, who went across the United States at its 40th parallel, studying the geology and natural history. One was George Wheeler, who explored much of the Basin and Range in Utah and areas around the Grand Canyon. Ferdinand Hayden went north and found Yellowstone National Park and made one of the very first geological maps of Yellowstone National Park, which has one of the largest concentrations of geysers anywhere in the world. And for our talk today, John Wesley Powell launched down the Green River from Wyoming and followed the Colorado River almost all the way to the end of the Grand Canyon over the course of about 5 months in 1869. Of the various surveys, his may have been the most famous at the time for a couple of reasons. Powell was a Civil War veteran. He had lost an arm fighting in the Civil War. And he went on to become an explorer of the American West. And it is not known for sure, but it has been proposed that his group was among the first to actually take boats through the Grand Canyon during their geological survey and explore it from river level. At this point in time, cameras had started to come into the fore, and these surveys, which lasted, Powell's was 5 months, but some of them lasted as long as 5 or 6 years, also took artists along to paint renderings of the Western United States. And these artwork and these photographs made their way back to the Eastern US, where they were published in newspapers, and it began to kind of stoke the American imagination of the geology of the Western United States. This is just a couple examples of this. On the left is a photograph of the lower falls of the Yellowstone River. This is in Yellowstone National Park in Wyoming, United States. The photograph was taken in 1871 and later turned into a color photograph by a famous American artist named Thomas Moran in 1872. The photograph there at the bottom right in 2024 is one that I took when I went to Yellowstone a couple of years ago. And you can see how they were capturing kind of the majesty of these landscapes that many people had never seen or imagined. The Grand Canyon in particular loomed large in this kind of imagination. The size and scale of this gorge were just beyond comprehension for many people. And so photographs like this one from Powell's survey, which was taken on the river level, looking up at the walls of this huge gorge, 1,600 meters deep at its deepest point, almost 26 kilometers wide at the top. And then the paintings, this one by William Holmes, were reproduced and painted this landscape that was just beyond the comprehension of many people, almost no vegetation, bright red colored rocks. And so the imagination of people just became overwhelming. They began to want to explore West and learn about the geology, geography, and landscapes of the western part of our country. I think it's no small coincidence that in the years just following these surveys, the Geological Society of America was founded in 1888 to capitalize on this interest in the geology of the Western U.S., in the interest people had in these surveys that had taken place just years before. And John Wesley Powell, who led this survey of the Grand Canyon, ended up becoming the first director of the United States Geological Survey and established that governmental organization which still exists to support geological study today. So the Grand Canyon is, as I said, iconic for its size. It's almost 26 kilometers across at its widest point from rim to rim. It's 1,600 meters deep at its deepest point, and it's about 450 kilometers long. It's carved by the Colorado River, which flows from the Rocky Mountains in Colorado out to the Gulf of Mexico, the Gulf of California in the country of Mexico. This picture here is from the south rim of the Grand Canyon looking across to the northern side. And one of the reasons I think the Grand Canyon is such an iconic spot in the Western United States or around the world is you actually can get up onto the rim of the canyon on either side and look down into the depth from the top. Many gorges of this size, you're in the bottom looking up with very few ways to kind of reverse that perspective. And so that perspective really adds to the incredible vistas that you get when you visit the Grand Canyon. But I'll talk a little bit about the stratigraphy of the Grand Canyon and what's encoded in the rocks that make up the Grand Canyon. You can see here the stratigraphy is largely flat lying. It's one of the remarkable things about the Grand Canyon we'll touch on a little bit later. And this layer cake stratigraphy covers a significant fraction of geologic time. It's just an aerial perspective of the Grand Canyon showing where it sits within the state of Arizona, northwestern Arizona in the United States, and a perspective on the size of this canyon. As I said, 445 kilometers long, over 25 kilometers wide, and 1.6 kilometers deep. Depending on how you count these things, and I don't know exactly how one does, this is the 8th largest gorge in the world, but certainly one of the largest and most impressive gorges anywhere on the planet today. So the Grand Canyon, as I said, has this beautiful flat-lying stratigraphy across most of its region. And that stratigraphy reflects and records the evolution of the Western United States and many of the significant geological events that have taken place through its geologic history. This is a picture from a place called Dead Horse Point, again on the southern side of the Grand Canyon, looking across towards the north. And you can see a couple really remarkable geological features in this photograph. I've drawn one here in orange. This is called the Great Unconformity. It's one of the classical pieces of Western U.S. and in fact U.S. geologic history. It sits right at the base of the Cambrian, so you have Cambrian rocks just overlying that orange line. And I've tried to show there with some white hashers the orientation of strata on either side of that unconformity. So you have an angular unconformity with rocks that are older than Cambrian below and rocks that are younger than the Cambrian above. This great unconformity can be found all across the United States, from California in the West Coast all the way to Wisconsin in the center portion of the country. And it represents the formation and sedimentation on a passive margin of the Western United States throughout much of Paleozoic time. I've shown here a little bit of a schematic diagram of the strata of the Grand Canyon. You can see that below that great unconformity, we have Neoproterozoic strata. They're called the Unkar group and the Chuar group. These are primarily Neoproterozoic in age. They sit in disconformity on top of granites and schists, known as the Vishnu schist and the Zoroaster granite. And then overlying them almost completely flat is not a complete in terms of time, but stratigraphically relatively full section of Paleozoic strata from Cambrian all the way up through Permian. The deepest part of the gorge in the Grand Canyon, called the Inner Gorge, is carved through these granites and schists. And then this Grand Canyon steps back in these big steps as it reaches these really significant resistant rocks, such as the Red Wall limestone or the Coconino sandstone. So you have this kind of stair-step pattern coming down the sides of the Grand Canyon. These reflect really key tectonic events in the history of Western North America. The Western U.S. basement rock is about 1.7 billion years old. when fragments of various terrains collided to the cratonic core of Western North America. And the Zoroaster granite and the Vishnu schist represent that collision and the building of continental crust underneath Western North America. That collision led to the assembly in part of the supercontinent Rodinia, and Rodinia rifted apart about 700 to 800 million years ago, and the strata below the Great Unconformity, the Unkar and Chuar groups, are reflective of that extensional breakup process, normal faulting and sedimentation as the supercontinent fragmented. After the supercontinent fragmented and the margin began to cool and subside, the whole rest of that package of Paleozoic strata represents a passive margin developing across the western United States, with first beach facies sandstones, and as the water went further inland, fine-grained deposits offshore, and eventually a large carbonate shelf, comprising many of the limestones one sees in the walls of the Grand Canyon today. So I'll give you a little bit of geologic context for the Grand Canyon. The Grand Canyon is on the edge of what is called the Colorado Plateau. And the Colorado Plateau sits across 4 states in the western United States, Arizona, Utah, New Mexico, and Colorado. And it's shown in this kind of orange shading in these two diagrams. The Colorado River kind of traverses the Colorado Plateau from northeast to southwest. And on the western edge of the Colorado Plateau carves the Grand Canyon before exiting the Colorado Plateau and flowing into the Basin and Range, and then eventually down to the Gulf of California. The Colorado Plateau is a unique feature in Western U.S. geology. If you look around much of the rest of the Western United States, it has a really quite complicated deformational history. In Mesozoic time, the Western United States is often described as an analog to the Andes today. There was subduction off the west coast of the United States. That subduction led to significant volcanism and the creation of a volcanic arc, perhaps similar to the Andes that makes up today the Sierra Nevada mountains in California. And then on the eastern side, of that volcanic arc was a folded and thrusted belt. We call that the severe fold and thrust belt. It's similar to like the pre-Cordillera of the Andes in South America. And so there was this large mountain belt that was constructed in the Western United States throughout much of the Mesozoic. And then throughout most of the Cenozoic, that process has unraveled, and the Western United States today is pulling apart. And it's leaving this pattern you see on this digital elevation model here of these basins and ranges, these mountain ranges and intervening valleys across a lot of Nevada and Utah, these north trending little worms crawling their way across the landscape. Somehow the Colorado Plateau remained largely unaffected by this complex tectonic history. It sits today at a mean elevation of about 2 kilometers. It has some, but modest, internal topographic relief, and it has little internal geologic deformation. The strata, as we saw in all those pictures of the Grand Canyon, is perhaps gently tilted, but it's not strongly deformed or distorted. This is kind of a really nice perspective diagram of the Grand Canyon and the Colorado Plateau. As I talked about in the Grand Canyon, we see this beautiful section of Paleozoic stratigraphy gently dipping off to the north. As you continue to the north from the Grand Canyon, you walk your way through Mesozoic stratigraphy and eventually even all the way up to Eocene stratigraphy, Paleocene and Eocene stratigraphy. The names on here are the names of some of these famous cliffs that, much like at Grand Canyon, are large resistant bands of rock that make these continuous ribbons of cliffs across the landscape. And then we have some of the famous U.S. national parks where one can go see all these various different pieces of stratigraphy, from the Grand Canyon to Zion National Park to Bryce Canyon. In the upper right here, I've kind of superimposed on this slightly folded block diagram all of the strata that were deposited on the Colorado Plateau throughout the Phanerozoic. The Paleozoic strata, which are highlighted in the lower part in blue, are what make up the Grand Canyon. When you get to the rim of the Grand Canyon, you're largely on top of the Paleozoic. But if you were able to continue walking north, you could eventually walk your way through a significant portion of Mesozoic strata, including Triassic, Jurassic, and Cretaceous strata, and even all the way up into some Paleocene, Eocene strata in places like Bryce Canyon National Park. So this stratigraphic package and the stratigraphic record tells us something about the depositional history, about the environments in which the Grand Canyon strata and associated strata of the Colorado Plateau were deposited. And in particular, I'll point out this one particular unit called the Tropic Shale or the Manco Shale, which is in the mid to late Cretaceous in the Western United States. And it consists of marine shales. It has fossils in it that are known to be of marine origin. It's particularly well known for turtles. And so one of the interesting things that this tells us about the evolution of the Grand Canyon region is the Grand Canyon was at sea level, more or less, throughout a significant fraction of the Phanerozoic, almost all of the Paleozoic and a significant portion of the Mesozoic. The rocks that were being deposited in the area where the Grand Canyon is today were below sea level or near sea level. And that even continues up through the rest of the Cretaceous, where there's kind of deltaic sediments, near shore brackish water facies. And so the Grand Canyon, instead of being at 2 kilometers, was sitting at sea level. And so in order to carve a 1,600 meter deep gorge in this part of the world, at some point we have to lift this part of the world up from sea level to nearly 2 kilometers of elevation so that we can carve this huge gorge back down through these strata. So a brief summary of what I've just mentioned. The Colorado Plateau was uplifted from sea level to almost 2 kilometers elevation since the Cretaceous because it has marine strata of Cretaceous age deposited on it. It did this in the absence of significant internal deformation. Often when we think about making high topography, we think about folding and deforming rocks, shortening them and thickening them and using isostasy to lift them up. The Colorado Plateau has to uplift in some other manner than that, which is a unique geological twist to their development that I won't dwell on too much today, but it's a very, very interesting aspect of it. We need to uplift the Colorado Plateau to 2 kilometers in order to carve this 1.6 kilometer deep gorge through it. And so that leads to some questions, which is, when was the Colorado Plateau uplifted? Well, we know it was after the Cretaceous, but can we say more than that? And then when was the Grand Canyon carved down into it? So I'll talk a little bit about how we go about trying to address these two different questions, which are related, but not exactly the same. So the first question is, when was the Colorado Plateau uplifted? When did these rocks that were at sea level get lifted to their modern elevations? Did it happen quickly? Did it happen slowly? Are there ways that we can try and assess that process, and doing so perhaps get an idea of what drove the uplift of the Colorado Plateau to its present day elevations? And to do that, scientists have applied some methods called paleoaltimetry, in which the goal is to try and figure out for sedimentary rocks that were deposited in the geological past, can we extract from those rocks some kind of signature, chemical signature, botanical signature, fossil signature, that tells us the elevation at which those rocks were at the time that they were deposited. Paleoaltimetry is challenging in many mountain belts because many mountain belts do not have a way to contain or collect sedimentary archives that would record past surface conditions. If one were to go to, for example, the Andes, there's very few basins that catch sediment in the Andes. Most is it's flushed out along major river systems, and so there is not a record of what of older strata preserved in the Andes during or throughout its formation. The Colorado Plateau, because it's relatively undeformed and relatively low relief, actually has sedimentary archives that we could potentially use to assess the elevation of the land surface at various points in the past. There are a variety of different techniques that have been proposed to try and understand paleo elevations. And obviously most of them require going to some rocks of an ancient age and trying to get from those rocks a proxy that tells us what elevations might have been. I've listed here about 4 different methods that various people have tried or various scientists have tried and developed, and they all rely on either trying to measure atmospheric pressure through some kind of record in the geologic strata, or by taking and trying to measure some kind of temperature from a proxy in the geologic strata. And so these have a variety of techniques. Most of them depend on some kind of sedimentary strata. So paleobotany is one way that people approach understanding paleoaltimetry. You look for large collections of fossil leaves. You look at a variety of things about those leaves, their size, their shape, their serration. And you try and take those from collections of dozens of leaves to try and figure out something about the atmospheric conditions and the climatic conditions in which that set of fossil plants would have lived. And then people take that information and try and go from climatic conditions to elevation conditions, understanding that temperature is a function of climate and of elevation. Stable isotopes are another method that people use to try and understand paleoelevation. They can kind of do that in one of 2 different ways. One is to understand that as air masses rise or are lifted up mountains, rain falls out, and preferentially heavier isotopes of water, heavier isotopes of oxygen and hydrogen are removed from those air masses. And so as the air masses get to higher and higher elevations, the water that comes out is isotopically lighter and lighter. If that water is then preserved in the geological record as shells or inorganic carbonate or soil carbonates, one may be able to glean some information about at what elevation those carbonates were formed, given the isotopic values of the water from which they may have been derived. A more direct method, which has been developed in the last couple decades, is the fact that when carbonate molecules form, they have the option to incorporate isotopically lighter or isotopically heavier molecules of carbon and oxygen. And it turns out the degree to which they choose heavier isotopes to incorporate into their atomic structure is temperature dependent. And so there's a hypothesis, or not a hypothesis, but there's a mechanism by which one can actually try and directly measure the temperature at which carbonates formed by looking at the clumping of heavier isotopes into particular molecules. And so people applied that to limestones, fossil shells, also soil carbonates, trying to understand what temperature they formed at and then relate that temperature back again to altitude. On the far left, I've shown one last idea, which is it has been proposed that by looking at the bubbles in basalt flows and looking at the difference in size of the bubbles between the top and the bottom of the flow, one may be able to actually directly measure directly measure atmospheric pressure, and from that invert for elevation. So these methods have been applied to the Colorado Plateau and the Grand Canyon. Shown just a couple examples of those here. On the left is a paper from Heitman et al., published in 2021, in which they have shown a compilation of paleo elevation estimates from rocks all around the Grand Canyon region. The Grand Canyon is there in the center of the image, and the Colorado Plateau is shown or surrounding it, using isotopic methods of both depleted isotopes as well as clumped isotopes. They've also looked at paleobotanical studies, collections of fossil plants, and they have some geological constraints they've incorporated as well. Their samples range from 70 million years old to about 6 million years old, and so the goal was to try and establish the elevation of the Colorado Plateau throughout much of Cenozoic time. Similarly, Dorksehagian and his colleagues used basalt vesicle paleoaltimetry to try and understand the elevation of the Colorado Plateau by looking at basalt vesicle sizes surrounding the Colorado Plateau. Unfortunately, given the ages of eruptions of lavas around the Colorado Plateau, their time range is much more limited, from 23 to 0 million years. And so since we're kind of interested in knowing that the Colorado Plateau is at sea level in the Cretaceous, I'm just going to focus briefly on the summary from Heitman et al. Of the paleobotanical and isotopic evidence that spans the Colorado Plateau and their estimates for paleoelevation. So this is a pretty complicated diagram that one often needs to sit down and wrestle with. But the simple summary of this diagram is that the black circles show the elevation of the sample as it was collected in the present day. And underneath it, the colored symbols show the estimated elevation of the sample at various points in the past, where the colors suggest how far back in the past that estimate was made. And so there's a couple of things to just draw out of this. The first is that the modern sample elevations are almost always the highest elevation, meaning that the Colorado Plateau is today as high as it's ever been. It hasn't been higher in the past and then subsided. The summary of these data by Heitman et al. Is that at least approximately a kilometer of surface uplift of the Colorado Plateau occurred between the late Cretaceous and about 38 million years ago. And it obtained its current elevation of about 2 kilometers sometime between 60 and 6 million years ago. They don't have a lot of, I'd say, precision on whether it happened quickly or slowly, but they do have this kind of at least constant or 2-part elevation uplift with an early phase and a later phase, or one could look at it as a continuous uplift to 2 kilometers over the majority of the Cenozoic. But it's been uplifting more or less since early Cenozoic time. So we've uplifted it. When did we start carving this canyon down into it? So I'll address a little bit how people have gone about trying to assess this question as well. So the first aspect of this question is really easy, and that is the minimum age of the Grand Canyon. And I really like this photograph taken from an airplane. And this is showing what's called the Uinkaret lava field. And it has these big basaltic eruptions, and the basalt lavas flow across the landscape and actually flow down the sides of the Grand Canyon all the way until they meet the Colorado River. Some of the biggest rapids on the Colorado River that are famed by people who raft down the river are formed by these lava flows. One is actually called Lava Falls. And so we know the canyon is at least 1 million years old, given the age of the lava flows. The canyon was there when these lavas erupted because they could flow down into it. But what can we do to assess the incision history beyond that? Well, one way we can try and do that is with a method called thermochronology. And thermochronology here just means thermo being temperature and chronology being time. And what I'm showing here is an isotopic decay scheme in which the elements uranium and thorium decay, and they, through decay, generate a child isotope of helium. The basic decay scheme, if you're not familiar with this, you may be familiar with through uranium-lead geochronology. Uranium decays to become lead. We use that to date zircons in the earth sciences and do the absolute age dating of granites and other igneous bodies. But a side product of this decay is the generation of alpha particles or helium atoms. And as uranium-238 decays to lead-206, there's an entire decay scheme, and along that way, helium or alpha particles are generated as the unstable element of uranium goes through a series of decays to eventually become the stable element, lead. And so it emits protons and neutrons and alpha particles, or just effectively helium with a mass of 4. And on the way from uranium-238 to lead-206, 8 of these helium atoms are generated. It turns out that uranium-235 decays to lead-207 and also generates helium. It generates 7 helium atoms. And thorium-232 decays to lead-208 and generates 6 helium atoms. So if you have a mineral that has uranium and thorium in it and they're undergoing radioactive decay, they will generate these alpha particles or these helium atoms. And helium is a really, really small element. And so it turns out that in a number of minerals, helium just escapes right out of the mineral at temperatures that are not particularly warm. This plot on the left here is what we call the closure temperature for various radiogenic systems we use to understand geologic time quantitatively. And what it's showing is for different decay schemes and different minerals, the child and the parent isotope are trapped into the mineral crystal at a particular temperature. So at one end of the spectrum here, if we look at uranium decaying to lead in a crystal of zircon, if the crystal of zircon is cooler than about 800 degrees C, the parent and the child are trapped in that crystal, and the radiometric clock starts, and it runs, and it calculates geologic time for us. At the other end of the spectrum are what we call low temperature thermochronometers. These are chronometers that we can reset the clock effectively by heating up the minerals to not particularly hot temperatures. And so the coolest of these is called the uranium, thorium, helium system, which I've just described to you, in the mineral apatite. And so if you have an apatite grain shown here in a little picture, these little stubby hexagonal prisms, and uranium's decaying in them and producing helium, if we heat these apatite crystals up to even 100 degrees C, the helium will just escape and diffuse out of the crystal. If we cool it down below about 40 to 80 degrees C, we will trap the helium in the crystal and start our geologic clock running. This is really crucial because these temperatures are temperatures that are quite common in the near surface of the Earth. So if you think about a geothermal gradient of 30 degrees C per kilometer, to get to 40 degrees C, you just have to go a little more than a kilometer down in the Earth to find 40 degrees C temperatures. And the Grand Canyon is 1.6 kilometers deep. So in theory, one might be able to actually look at the cooling of the rocks at the bottom of the Grand Canyon using low temperature thermochronometers such as the one I've described here. And so the idea is here we have the surface of the Earth, and we have these isograds of temperature below the surface of the Earth. Obviously, temperature is increasing downwards towards the center of the planet, but these isotherms are 40, 60 degrees C are only within a kilometer or two of the surface of the Earth. And so if we begin carving something like a Grand Canyon, then our rocks move towards that surface and will cool through these various isotherms. And as they cool through the 60 to 40 degrees C isotherm, our clock will start. And maybe we can measure the time at which the rocks above them were being eroded, cooled, and removed. So lots of people have had the idea to try this in the Grand Canyon. This map here, every red dot is a sample that somebody has collected and tried to apply one of these low temperature thermochronologic techniques to try and look at the carving of the Grand Canyon and its denudation or exhumation history. The various studies are listed there on the right. And as always happens in fun and complicated parts of the world, two kind of distinct end member interpretations of the data have arisen. One says that the Grand Canyon is old. The canyon as we know it today was carved as a whole in Cretaceous time, or certainly started to be carved in Cretaceous time as the Colorado Plateau was uplifting, perhaps from an eastward flowing river, leaving that Andean-style mountain range that existed on the west coast of the U.S. at that time. Another group interprets the data quite differently. It's that the Grand Canyon was carved in segments, and there may be portions of the Grand Canyon that are old and part of older river systems, but the modern canyon as we see it today with a single river flowing through it really only integrated in the last 6 million years along the modern Colorado River, and overall the Grand Canyon that we see is a young geographic and young topographic feature. Fortunately, or perhaps not fortunately, we have other ways that we can try and assess the timing of the carving of the Grand Canyon. We can look at geomorphology, we can look at fluid inclusion studies, we can look at stratigraphy around this part of the world. We can look at cave deposits and the ages of cave deposits down the Grand Canyon wall. And we can try and take those other pieces of evidence and bring them to bear on the problem of when did the Grand Canyon get carved. Well, it turns out those individuals who pursue those studies find out that they are just as diverse in their opinions as the results from thermochronology, with some finding that the Grand Canyon is clearly Miocene or Pliocene and integrated at that time. The geomorphology is consistent with the beginning of the Grand Canyon integrating at 6 million years. and others saying that their results are certainly compatible with formation in the late Cretaceous and incision and exhumation at that time. So I'll summarize here that the Grand Canyon is one of the largest gorges in the world. I think that the thermochron data and other data are telling us, and the uplift data, that regional denudation of the Colorado Plateau appears to have begun synchronously with its uplift from sea level to 2 kilometers in late Cretaceous or early Cenozoic time. The late Cretaceous exhumation is recorded by fluid inclusion studies and low temperature thermochronology, but whether this exhumation reflects the establishment of the Grand Canyon as the geographic entity that we see and recognize today at 60 million years ago, or whether that entity was established much more recently in geologic time, remains a matter of ongoing study and continuous debate. So thank you very much. I'm happy to take any questions that you may have.
Thank you so much, Professor Nathan, for your talk. It's a quite interesting question theme. And I didn't realize that you guys have this question about the timing of formation of the canyon. So we have a lot of people thanking. Thank you for the presentation.
Sure.
Trying to put here. And do you have some comment, Murilo?
Well, it was a very good presentation. Super interesting. I think that we all Brazilians will have a culture here that we see a lot of movies from the United States, and we see the Grand Canyon all the time. So it's pretty interesting for us to see about the geology of that area. I was just wondering, because the structure is very similar to other parts in the world. I think Namibia has a very similar area formed by a river as well. Do you know this area there?
I don't know the geology of Namibia particularly well. I do know that if the things that they do have in common, certainly, they're both obviously very arid, so the rocks are exposed very well. And in particular, what both the Western United States and Namibia have are beautiful exposures and relatively continuous exposures of rocks from Neoproterozoic into Cambrian time. In the Western United States, you have to go a bit further west of the Grand Canyon to find those. But people in particular who want to study the period of time called the Ediacaran and kind of want to understand this transition from, soft-bodied organisms to, the fossil record that is much better preserved because they now have shelly material. That's kind of a crucial time people look at. And in the Western United States and Namibia, I know, are both world-class places one goes to try and study that, that kind of history of early life and that Cambrian explosion of life, or at least Cambrian explosion of preserved life.
Thank you.
Thank you. And I guess it's not simple to obtain apatite grains or to do these studies.
Is it difficult, did you ask?
Yes.
It depends on the rocks that you're working with. So if one were down in the inner gorge of the Grand Canyon and one were to go sample the Zoroaster granite, many silicic igneous rocks have apatite in reasonable quantities, such that if you collected a couple kilograms of granite, you would be able to, or granodiorite, you would successfully be able to obtain enough apatites for this study. Obviously, in the walls of the Grand Canyon, a lot of those rocks are carbonate or limestones. You're not going to recover any apatite from those. And then the sandstones, it all really depends on the source or the provenance of the sandstone. So, some will be quite rich in apatite, and others will not be.
Okay, thanks. Paulo Ernesto has a question. Primeiro, ele agradece. Thank you very much for your presentation. And here's the question. Is there any relationship between Grand Canyon uplifting and the Sierra Nevada uplifting?
Yeah, that's a really interesting question. There's a couple interesting relationships maybe between those. I think the Grand Canyon area, Colorado Plateau area, was potentially uplifting a bit earlier in geologic time. But something that's been proposed for both the Sierra Nevada and the Grand Canyon as a cause of uplift is, as I talked about earlier, lots of times when we see high topography, what we think about is the crust shortening and thickening, and that thickened crust floating higher on the mantle through isostasy to make high topography. Both the Colorado Plateau and the Sierra Nevada, that's a challenging way to make the topography because there's not much evidence for significant horizontal shortening. So in both cases, a change in the density structure of the crust has been proposed as the mechanism for uplift of those mountains. In the Sierra Nevada, particularly the southern Sierra Nevada, the loss of a very dense eclogitic keel from the bottom of the Sierra has been suggested as a reason it has uplifted. And a similar mechanism has been proposed for the Colorado Plateau, where a change in the lowermost part of the crust, a chemical change to being less dense, is what actually in part led to the uplift of the Colorado Plateau. So they're both kind of interesting. They may have mechanisms driving their uplift that aren't, they are isostasy because their density changes, but that they're not the typical things we think about in terms of crustal thickening.
Oh, thanks. And we have other comments. Thank us for the presentation. Thank you so much. And a comment from Sean O'Brien. I love the paleobotany contribution to our understanding. We used paleobotany as a much smaller time scale to recreate the landscape at historic sites in the U.S., dating only back to the 1700s.
1700s?
Hundreds, yes, some centuries.
Paleobotany is a really powerful tool. The challenge with paleobotany is people tend to the other methods because you can go to almost any stratigraphic section and find some amount of carbonate that you can do isotopic analysis on. And to do paleobotany, you need collections of dozens or hundreds of leaves. And so the odds that you find that at the right time slice that you want for your study is the real challenge. Whenever you do, it's just wonderful to go work with that kind of data, but unfortunately you can't ever predict that you will. And that's, I think, one of the kind of challenges of paleobotanical approaches is that really rich fossil plant sites are hard to find.
Yes, and Paulo Ernesto comments that there are some volcanic flows in Sierra Nevada as demonstrated in Grand Canyon to support what you told us.
Yes, yeah, there are large lava flows that flow all the way down the western slope of the Sierra Nevada, and in fact, the comment I made earlier about the loss of this eclogitic root from underneath the Sierra Nevada is known in part from xenoliths that are brought up or not brought up in volcanic eruptions of various ages. And so older volcanic eruptions that come through the Sierras bring this deep eclogitic root. Younger lavas don't have that anymore. And so that's one of the reasons they think the root may have delaminated and peeled off into the mantle in the last few million years.
Okay. Yeah, that's why he asked you. So, well, by now we don't have any questions. I don't know if Steph wants to tell us something about the team.
So,
No, just to thank you all. I mean, it's lovely, a lovely presentation and a lovely occasion. And I hope we have more of these.
yes, thank you so much for the invitation. I'm very honored to be able to talk to everybody today and to meet with you.
Thanks so much, Professor Nathan, for coming, and for you and Esther for our partnership. And I hope we have another events like this one. Muito obrigada, professor Nathan e professora Esther, pela apresentação, pela presença e pela nossa parceria realizada, né? E que venham novos frutos a partir, né, desse nosso acordo. Murilo, quer comentar ainda alguma coisa?
Just to finalize, it's been a year, more or less, that we signed the partnership, and we're already having this integration, these meetings. So we really hope to have these more and more often in the next few years. And I think this interaction is very important for our societies. So it's a win-win for
very
us.
much so.
So thank you so much for your time. It was a very interesting lecture, and I'm really excited about the future.
Great. Yeah, thank you so much.
Muito obrigado.
Muito
And my
obrigado.
future includes to meet the Grand Canyon someday.
Yeah.
Thank you so much for your presentation. Muito obrigada. Bom, pessoal, só para finalizar, our next presentation will be with the Associação Geológica de Argentina. Será no dia 13 de outubro. Esperamos encontrá-los. A gente vai seguir com o nosso Giro pelas Américas, com o apoio do Confea, mais gente aqui ainda agradecendo, e agora eu vou deixar vocês com o vídeo da nossa patrocinadora, o Sistema Confea, e agradecer mais uma vez aí. Have a good night. Thank you so much.
Have a good one. Bye-bye.
Bye-bye. Vou eu fechar aqui.
Brasil terá déficit de 530 mil profissionais de tecnologia até 2025, mostra estudo do Google.
Déficit de engenheiros no Brasil chega a mais de 75 mil profissionais.
Um levantamento do Google for Startups sobre a escassez no mercado de TI aponta que a ausência de tecnologia, entre outros fatores, tem impactado o setor.
Você está pronto para ser o agente transformador no nosso país?
Nosso futuro é feito de pessoas se comunicando e capacitando umas às outras para fazer mudanças reais em nosso país.
Mas para essas mudanças acontecerem, nós precisamos agir. Afinal, para a inovação e sustentabilidade andarem juntos, é preciso tecnologia.
E para o Brasil se desenvolver, é preciso engenharia, agronomia e geociências.
Você está preparado para ser o agente de transformação que o país precisa para crescer?
Te convidamos a caminhar com a gente em direção a um novo momento da nossa profissão.
Chegou a hora de nos transformarmos em protagonistas dos projetos que podem mudar a vida das pessoas do nosso país.